In about 4 billion years, or slightly more, our galaxy will collide with the Andromeda Nebula. It will be a grand dance of two cosmic giants, resulting in the formation of a new massive elliptical galaxy. Sometimes it's called the Milkomeda, seemingly calming the listeners. Scientists usually say that the distances between stars are so vast that during galactic collisions, the stars will simply pass each other by, and there is nothing to fear. However, truth be told, stars collide within our own galaxy right now without any Andromeda, and the consequences of these collisions are visible for tens of thousands of light years. Astronomers had predicted the closest stellar collision in 2022. As if that weren't enough, we are talking about components of a binary star. The researchers stated that the collision's flash would be visible to the naked eye. How likely is a stellar collision? Stellar collisions are far from the most frightening events that can occur when large galaxies collide. For example, there will be many supernova explosions due to starburst activity, and the merging core of the future galaxy can turn into something like a quasar, which also presents many problems for all living beings. However, for some reason, people are particularly afraid of collisions with alien stars, and scientists reassure them, saying, "Don't worry, everything is okay." The nearest neighboring star is more than 4 light-years away, which is around 30 million times the diameter of the Sun. They will simply pass each other by. Live peacefully and don't worry about these 4 billion years. The question is not whether stars collide, but rather how often it happens. The answer depends primarily on the region of the galaxy we are talking about and how closely the stars are located. First, let's consider the area close to the Sun. The density of stars here is relatively small. According to the catalog of nearby stars, within a radius of 15 light-years from the Sun, there are only about 60 stars. But the relative motion of stars concerning each other is also essential. The smaller the relative velocity, the higher the probability of a collision. Assuming that the relative velocity of stars in the solar neighborhood is about 20 kilometers per second, the average time between collisions of two individual stars is significantly greater than the lifespan of most galaxies. This means that stellar collisions with the galactic disk occur infrequently. For example, the Sun will come close to one of its neighboring stars only once in a million years, and a distant star will pass within 17,000 astronomical units from the Sun. While this may seem relatively close, it is still far from any actual collision. However, there are places where stars are much more densely packed, such as in globular clusters and the center of the galaxy. In the dense stellar core at the center of our galaxy, the size of which is only about 0.15 to 0.4 parsecs, the density reaches up to 700 million times the mass of the Sun per cubic parsec. In typical globular clusters, the density is slightly smaller, but still impressive, up to 1,000,000 times the mass of the Sun per cubic parsec. Consequently, stars in these regions are much closer to each other, leading to a higher likelihood of encounters. During a globular cluster's lifetime, up to 10% of stars in its central region may experience at least one close encounter with a neighbor within a few stellar radii. While this kind of collision is far from being a cosmic traffic accident where stars randomly crash into each other, the probability of a head-on collision between two stars is still exceedingly low, even in the dense space of a globular cluster. Instead, during close encounters, stars interact through gravitational forces. They exchange energy, alter their motion and velocity, and if they pass closely enough, they can form a binary star system due to tidal deformations. Later, these stars might merge. The key is to ensure that their relative velocities are not too high for a successful merger to occur. If a star passes by a binary or multiple star system, it becomes even more sensitive to such encounters, as it becomes a much larger target than a single star. Several scenarios can unfold during such events. The star may disrupt the binary system, breaking the gravitational link between its components, or it may eject one star from the pair while taking its place in the system on a different orbit. Sometimes, such interactions can destabilize the binary system and lead to its merger with another star in the cluster. Alternatively, the guest star may actually tighten the bond between the binary components, causing them to get closer before flying away. Regarding globular clusters, numerical simulations show that wide binary systems gradually become wider, and close binaries, on the contrary, tend to merge over time. Moreover, after the stars exhaust their hydrogen reserves, they expand as giants, which, as we will see, only accelerates the process. So, life is not easy for binary and multiple star systems in clusters. According to estimates, only 10% of them survive from their initial number, while the rest either dissolve or merge. Dynamic simulations of clusters show that about half of the binary star systems dissolve, mainly due to the influence of neighboring stars, while slightly fewer numbers of stellar pairs merge. In the end, only a very small fraction of double systems leave the cluster. Now, if we return to the vicinity of the Sun, as I mentioned earlier, stellar collisions are infrequent. However, for such collisions to happen, we need double star systems, and it's desirable for the distance between their components to exceed 1,000 astronomical units. Such star pairs are called wide binaries, and they are actually very large targets for neighbors. When a neighboring star approaches such a wide binary, there is a possibility that the orbits of the binary's components will change, becoming more elongated. In some cases, the companions might collide. However, considering the tidal interactions between stars, when they come very close and lose energy on deformation and heating of each other, their elongated orbits might round out, and the average distance between the pair might even increase. In this case, a collision is likely to be avoided. Nonetheless, according to estimates from this publication, such collisions occur approximately once every several thousand years in the galactic disk, in regions of relatively low stellar density. However, in colliding galaxies, these events might occur much more frequently. Now, if we add tight binary systems that gradually approach and collide, or double and multiple stars, which are even more sensitive to their neighbors, collisions and mergers happen much more often. But what happens to stars when they collide? Modeling direct head-on collisions of stars at high speeds is quite challenging, although intuitively we understand that it would disrupt the equilibrium between matter and gravitational forces. Inside stars, this would lead to changes in the rate of nuclear reactions in the core, resulting in a sharp alteration of energy output and the entire internal structure of the star. The chances of stars surviving such collisions without being completely destroyed are quite variable, depending on their masses, velocities, internal structures, and other factors. However, direct head-on collisions are extremely rare, and we are unlikely to witness them in the foreseeable future. On the other hand, stars in binary systems can collide, for example, due to the approach of some third star. Three's a crowd, a motto for stars. Or in some cases, they can merge even without external influence. In general, a star pair can exist for quite a long time, millions and billions of years, regardless of whether it was initially a binary system or became one due to the passage of a nearby star. If at least one of the stars in the pair is massive enough, it will eventually start turning hydrogen in its core into helium, becoming a red giant. And if it fills its Roche lobe, the material from its surface will start to flow onto the neighboring star. Then again, there are various possibilities. The red giant stage can end with something compact, such as a white dwarf, a neutron star, or a black hole. But the fate of a red giant can be influenced by its neighbor. It's the most standard scenario for the life of a binary star, but not the only one. For example, sometimes the orbit of a pair starts to shrink due to stellar winds carrying away orbital momentum. In such cases, the two stars merge into one even before one of them becomes a red giant. Another scenario involves the situation where the envelope of a giant star is much larger than the distance between the stars, and after one of the stars expands, they will rotate within a common envelope. It can also happen that stars in a binary system eventually fill both Roche lobes and touch each other's surfaces. At that moment, the binary star resembles a peanut, and this is called a contact binary. Material that no longer fits into the Roche lobes of both stars will be ejected outward, enveloping the pair. Modeling shows that this envelope gradually leaves the system, carrying away angular momentum from the rotating stars. As a result, they get closer to each other, causing even more intense loss of matter. This creates a positive feedback loop. the closer the stars get, the more material they lose together, which brings them even closer, and so on. The further development of events depends on the parameters of the stars themselves, such as their mass or mass ratio to each other. Also, the types of stars involved matter. The system can consist of red giants, white dwarfs, or normal stars that are still burning hydrogen. The vast inflated envelope of a red giant is weakly gravitationally bound to its core. If a sufficiently massive giant collides with it, the giant will shed its envelope, resulting in a sort of incomplete merger. The finale would be an even closer binary star, and the extensive envelope would be ejected from the system. In the case of a normal star, not a giant, the density is much higher. Therefore, dense matter more effectively slows down the collapsing neighbor. As a result, the merger happens faster, and one star won't spin within the other for long, scattering its material. In this case, a common envelope may not even form. Some models show that this process happens very explosively when the mass ratio of the merging stars is not too small, but not too large. If a very small star, or even a planet, falls onto a star, its gravity won't be enough to eject the envelope from the system. If the colliding star is too massive, its gravity will cause the envelope to move almost synchronously with the stars, making it fly outward. However, modeling shows that at the final stage, the star, which was slowly approaching its partner in a waltz, literally plunges toward it. At this moment, the entire system flares up with the energy of hundreds of thousands and millions of suns. It should be the most energetic and high-speed event. Astronomers observed such outbursts on September 2, 2008, a bright red nova, a result of a collision. Astronomers noticed a flash designated as V13.09 Scorpii. At first, they mistook it for a regular nova flash, a thermonuclear explosion on the surface of a white dwarf. However, it turned out to be a different type of flash called luminous red nova. Luminous red novae are distinguishable from regular novae by being much brighter, with luminosities hundreds of thousands to millions of times that of the Sun at the peak. They exhibit a very unusual brightness behavior. Initially, there is a very strong outburst with a spectrum indicating material moving at extremely high velocities, hundreds of kilometers per second. Then, after a decline in brightness, it suddenly stabilizes, and the star almost does not fade, emitting red light for hundreds of days. Hence the name luminous red nova. The observations provided valuable insight into how stars merge. The bright flash right after the merger is the fastest and hottest material that emerges from the star after the collision, similar to water droplets that splash when a stone is thrown into it. The slower and red glow is explained by the remnants of the star's envelope into which the neighbor star fell. These layers cool down and re-emit the energy acquired during the fall, similar to some supernova I mentioned before. The emitted radiation comes from the expanding shell region, where the temperature drops to about 4,000 grace, resulting in a red color. The shell expands and seems to pass through this temperature boundary, and from there, the radiation reaches us after electrons merge with protons, forming hydrogen and releasing energy. Unlike the shell itself, this temperature boundary almost does not shift, so many days after the flash, the new star maintains a constant brightness and red color. The main explanation for luminous red novae is the merging of stars. One famous example is V838 Monocerotis, which flared up in early 2002. It became famous for the beautiful light echo animation, demonstrating the incredible gas expansion and the reflection of the flash's light from earlier material ejections. Also, initial diameter measurements of V838 Monocerotis after the flash revealed it to be one of the most extended known stars, a supergiant with a diameter comparable to Jupiter's. However, subsequent measurements showed that the star was somewhat smaller in size, similar to Betelgeuse, a red supergiant. Nevertheless, it was interesting to note that before the merger, the star was originally classified as blue, class B, and its current appearance is temporary as its internal structure has not yet reached equilibrium. So, stars are merging. The final act of this process can be quite turbulent, and the bright red nova is evidence of that. But what will be the result of such a merger? Perhaps one of the most common outcomes of stellar collisions or mergers is a blue wanderer. Well, it's an old joke about them. I mean, stars. It's easier to find a blue wanderer in a globular star cluster. All the stars in a globular cluster formed at roughly the same time, but the more massive stars burn through their hydrogen faster than the lighter ones, becoming gas giants. So stars on the Hertzsprung-Russell diagram will be along this line called the main sequence. When the hydrogen runs out, the star leaves the main sequence. And since all stars in the cluster are the same age, they should all leave the main sequence simultaneously. First, the most massive and brightest ones, then the lighter ones, and so on. Consequently, the stars on the diagram will appear to bend towards the giants, and the older the cluster, the lower the bend. It is logical to assume that there should be no stars after the point of comfort. After all, they are all giants. However, blue wanderers are there, and they can form in two ways. The first is through a collision with a neighbor. The relative velocity of stars in a cluster is quite low, but the density is high. Therefore, a dangerous encounter can lead to their merger, resulting in a blue wanderer, a star that extended its life by receiving hydrogen from its neighbor. The second way is related to the evolution of stars in a close binary system. For example, they can lose rotational energy due to the stellar wind and gradually approach each other in a spiral. Or one star in the pair evolves faster than its companion and starts turning into a red giant. If the stars are relatively close, mass transfer can begin from the more massive swollen star, which is in the giant stage, to the smaller one. If this process continues for a long time, the smaller star may end up more massive, and again, it becomes a blue wanderer. Apparently, there are even more blue wanderers formed by this method. However, sometimes it is a collision that leads to their creation. Research in recent years shows that blue wanderers still hold many mysteries, and they can surprise us. For example, in 2019, results of a simulation of a merger of stars with masses of 7.8 led to the formation of a star with a mass of 15 solar masses. It makes sense, but what's remarkable is that it had a very strong magnetic field, up to 10^8 Gauss, which is 18 orders of magnitude stronger than the original stars had. If the magnetic field created at the center of this star remains until the moment of the supernova flash, then the compact remnant of such a flash would have a magnetic field of up to 10^16 Gauss. So, this could be a scenario for their formation. A white dwarf eats its neighbor and becomes a giant. But let's suppose the merger involves an unusual star or a red giant, and the remnant is a stellar remnant like a white dwarf. Or even better, two of them, just to be sure. If the mass of the resulting dwarf exceeds the Chandrasekhar limit, it will result in a supernova type 1a. However, if it's less than that, astronomers have been observing one strange star for centuries from the constellation Northern Crown. It's a variable star, meaning its brightness changes. It belongs to a rather rare type of variable stars called R Coronae Borealis. Usually, they are yellow supergiants, quite hot, sometimes hotter than our Sun, although there are exceptions. But unlike normal supergiants, they have practically no hydrogen lines in their spectra. There's a lot of helium, nitrogen, carbon, silicon, oxygen, and in some of them, a noticeable amount of lithium. The absence of hydrogen is a very strange feature, as usually even in the later stages of their lives, the outer layers of stars remain hydrogen-rich. These stars extinguish unpredictably and dim by several magnitudes. Interestingly, these changes occur in the visible range, but they are not as radical in the infrared. The reason for this behavior is dust, like from a campfire. Due to powerful convection, the star ejects material, including carbon. When it cools down to about 1500 degrees Celsius, it starts condensing into small dust particles, which efficiently absorb visible light. Each such ejection obscures the R Coronae Borealis star for a while until the dust disperses or moves out of the line of sight. But here's the question: how can a star, especially a supergiant, exist without hydrogen? Currently, there seem to be two main ideas, but both come down to the fact that it's not entirely a supergiant anymore. According to one idea, R Coronae Borealis has already shed its hydrogen envelope. It might have even created a planetary nebula around itself and found a little more helium, reigniting in the process. According to another idea, it was originally a binary system with two white dwarfs, a carbon-oxygen and a helium one. One day, the system lost energy and the white dwarfs collided. However, their combined mass was still insufficient for a Type 1a supernova. But after the merger, the object obtained a sufficiently high temperature and a lot of helium from one of the dwarfs. As a result, nuclear reactions resumed in it, and it stopped being a degenerate dwarf, puffing up to become a giant star, not red but yellow. Its powerful collective shell periodically ejects heavier elements than hydrogen and helium. This accounts for the dust. According to estimates, the lifespan of such a star is relatively short, about 57,000 years. Then, it will compress again into a small degenerate white dwarf. Sometimes, a collision between stars or a merger with a compact object can lead to a supernova. For instance, in 2017, during a sky radio survey in Laos, astronomers discovered a bright radio source that wasn't there before. They called the object this way, almost like Elon Musk's child. Upon further observation at different wavelengths, they found that the bright radio emission was coming from the outskirts of a dwarf galaxy with intense star formation, about 480 million light-years away. Analyzing data from other instruments, scientists detected an X-ray burst from the same object as far back as 2014. Thanks to extensive past observations, they reconstructed the scenario. It turned out that it was a pair of a massive star and a compact object, not yet clear if it was a neutron star or a black hole. The orbit of this compact pair steadily decreased over about 300 years. About 300 years ago, the compact object entered the atmosphere of its neighbor without causing a blast. The gas ejected during the merger formed a massive, thick toroidal ring around the pair. Meanwhile, a black hole or neutron star broke through the core of the companion star, disrupting the process of nuclear fusion. This led to the core's collapse, and the X-ray emission captured by MAXI originated from a jet shooting in opposite directions from the collision site. By this X-ray flash, scientists could precisely date the supernova explosion. In any case, both stars probably exploded as supernovae, given their massiveness. But in this case, it's crucial to note that the supernova was caused by the merging of the stars. Another possible outcome of stellar mergers is the Torn-Jitkov object, one of the most mysterious results of a merging in an evolved binary star system. Unlike blue wanderers, these objects were not observed directly. They were predicted theoretically, and it was Kip Thorne who received the Nobel Prize in 2017 for this work. The object represents a neutron star surrounded by a massive gaseous envelope, much like a typical red giant or supergiant star. In the past, it was a binary system in which the neutron star delved into its companion, effectively replacing its core. Thorne and Jitkov showed that with a specific ratio of the neutron core's mass to the surrounding envelope, the object becomes stable for timescales of up to 100 million years. This is a highly unusual phenomenon. From the outside, they might seem like red giants at first glance, but Thorne objects would be even redder. In fact, they should be the reddest stars in the universe, albeit only slightly redder than red giants. This difference is so subtle that it could be easily mistaken for reddening due to light absorption by interstellar matter or differences in the chemical composition of different stars. According to models by Thorne and Jitkov, these objects should have an unusual chemical composition. The temperature near the neutron star's core reaches 1 billion degrees Celsius, leading to intense nuclear reactions, something quite different from typical stars. The substance inside boils, similar to how the material boils from the core to the surface. This phenomenon might release the products of these unusual reactions relatively quickly to the object's outer boundary, and this could be observable. Thorne and Jitkov hypothesized that a noticeable difference in the object's composition compared to a star would be in the unusual content of carbon and oxygen isotopes, especially in the spectrum. Studying the molecular lines of carbon monoxide, vanadium oxide, and titanium oxide might reveal these distinctions. In more recent articles, this aspect has been clarified, and it is now considered that the main feature distinguishing Thorne-Jitkov objects from red supergiants will be the unusually strong lines of these elements in the spectrum. Estimations suggest that there could be 20 to 200 such objects in our galaxy, and over the past decade, Torn-Jitkov objects have been discovered and dismissed several times. For example, in 2014, a star in the Small Magellanic Cloud was found, with an atmosphere exhibiting an anomalous content of these heavy elements, closely resembling what was expected for a Torn-Jitkov object. In 1964, another group of scientists recalculated the star's parameters, closing the discovery. They proposed their candidate instead, but its status remains uncertain. The quest for Torn-Jitkov objects also extends into gravitational wave astronomy. For instance, in the event G1T08.4 Torn, a black hole with 23 solar masses merged with an object weighing 2.6 solar masses. However, the nature of this object, whether a neutron star or a black hole, remains unclear. For neutron stars, 2.6 solar masses are too large, as no neutron stars of such mass have been observed. On the other hand, it might be too small for a black hole. If this object is indeed a neutron star, it could have formed from a Torn-Jitkov object, where the neutron star accumulated mass by consuming its surrounding envelope. However, these are all mere speculations, and the search continues. Regarding the merging of neutron stars, I think many still remember it. There were numerous detailed analyses, so I'll be brief and just remind you of one event in August of the 17th year. The gravitational detectors of the LIGO-Virgo network recorded the signal G170817, which originated from the merger of two neutron stars. The region from which this signal came was determined quite accurately, allowing telescopes, both ground-based and space-based, to be quickly directed there. This was the first time in history that a cosmic event was observed in both gravitational waves and light. The merging of neutron stars was accompanied by a so-called kilonova flash, approximately 1,000 times brighter than a regular nova, hence the name kilonova. The Fermi and integral space telescopes also detected a short gamma-ray burst just after G787, and astronomers understood what caused all these observational phenomena. Thanks to observations in different spectral ranges, they were able to reconstruct the picture of what happened. In total, the two merging neutron stars had a combined mass slightly less than 3 solar masses. A small portion of this total mass was ejected during the kilonova explosion. It was also possible to estimate the amount of heavy chemical elements ejected during the merger, and it turned out that merging neutron stars are the primary contributors to the creation of gold, uranium, and other rare and heavy elements. As for the object formed after the neutron star merger, the most basic version suggests that it was initially a supermassive neutron star, but collapsed into a black hole approximately 300 seconds after the merger. However, there are other hypotheses. Some researchers believe that a long-lived heavy neutron star could have formed as a result. Further observations of such mergers are needed to clarify these possibilities. However, in the next occurrence, the LIGO-Virgo Observatory once again detected a gravitational wave signal from the merger of neutron stars, but this time no other observable phenomena, such as a kilonova, followed. As a result, statistics on such events are accumulating very slowly. So what about the collision in 2022? The one expected to occur around 2022 involves a system in the constellation Cygnus. It is a contact binary, meaning two stars are so close that they touch and exchange material. In 2017, an interesting study claimed that the orbital period of this pair is decreasing, indicating that the stars are approaching each other. A similar phenomenon was observed in the case of the progenitor V3009 Scorpii, which eventually erupted as a bright red nova in 2008. So, it is possible that something similar might occur in this system around 2022. However, astronomers are advised not to rush and prepare their telescopes just yet. Another group of astronomers rechecked these results by adding data from earlier observations that accidentally captured this star. And with these new data, it turned out that the orbital period of this pair didn't consistently decrease. In some moments of observation, it even increased, which puzzled astronomers. They had to dig into archives of observations of this star dating back to the 1930s, using old photographic plates to understand its behavior over an extended period of time. It was found that the period of this close pair varied, sometimes increasing and sometimes decreasing, during this entire time span. The exact cause of this behavior isn't entirely understood. It could be related to the fact that the pair is losing material while its components interact, but the specifics are yet to be comprehended. Further observations are needed to make sense of this peculiar behavior, and once something interesting is found, we will certainly share it here. Absolutely all galaxies, except for our own, are extremely distant astronomical objects. We will never truly know what happens in these immense gravitationally bound systems and the stars within them. Unfortunately, I will never have the chance to visit them. We can't send an umbrella or any device there. We won't know if there is life or wondrous forms of life. The universe, unfortunately, has taken away that possibility from us because colossal distances separate us. Galaxies are scattered throughout the entire universe. Nevertheless, we are grateful since one of these galaxies once gave us life, and now we observe them since time immemorial. Each of the galaxies is currently living its own life cycle. They collide, merge with others, evolve in their unique way, die, and are reborn. Each of them is distinct and peculiar. Almost everything you know about objects in the universe, planets, stars, moons, nebulae, is located within galaxies. They have become a peculiar haven for everything. To start, it's worth noting that the number of galaxies in the observable universe is genuinely unknown. However, with the naked eye, we can see 4 whole galaxies in the sky. They are the Andromeda Galaxy, the Large and Small Magellanic Clouds, and the M33 galaxy in the Triangulum constellation. But despite being able to see the contours of galaxies clearly in the sky or in photographs, in reality, galaxies do not have clear boundaries. It is not possible to precisely determine where the galaxy ends and intergalactic space begins. In the optical range, a galaxy may appear to have a certain size, but when measured using radio observations of interstellar gas, its radius can turn out to be much larger, and this is not uncommon. Typically, the size of a galaxy is understood as the photometric size, which is represented as a certain curve on its illuminated surface, connecting points of equal brightness. The measured mass of a galaxy will depend on its size. Firstly, there is the core. The core is a small region at the center of the galaxy. When we talk about galaxy cores, we often refer to active galactic nuclei, where processes cannot be explained by the properties of stars concentrated in them. In such cores, processes occur that release an enormous amount of energy. Common signs of activity in these cores include the ejection of ionized gas or high-powered radio emission, though not always. Often, the unusual behavior of active galactic nuclei is associated with supermassive black holes, and currently, this is the most widely accepted theory. The second component is the galactic disk. The galactic disk is a relatively thin layer where most of the galaxy's objects are found. It is a component in the lens of visible and spiral galaxies containing spiral arms. The disk predominantly contains younger stars compared to the galactic bulge, and their motion is well ordered. They revolve around the center of the galaxy in nearly circular orbits lying in the same plane. Galaxies have a high density compared to their surrounding physical components, like the halo or bulge, which are populated with older stars. In the disks of galaxies, often, spiral arms can be observed, radiating from the center of the galaxy, where the density of interstellar gas and young stars is particularly high. It is within such a spiral arm that we live. Next, let's talk about the so-called galactic halo, a term used in astrophysics. The galactic halo is an invisible component of a galaxy and is hypothetical in nature. Essentially, the galactic halo is the outermost part of the galaxy that greatly interests scientists, as studying it can help understand where the gravitational influence of one galaxy ends and another begins. Another galactic component is quite rare and is known as the polar ring. For example, the galaxy NGC 465a has this component. In the classical case, a galaxy with a polar ring has 2 disks rotating in perpendicular planes, with the centers of these disks coinciding. However, the exact cause of the formation of polar rings remains incompletely understood. Galaxies with polar rings are a type of galaxies where an outer ring of gas and stars rotates over the poles, and these polar rings are believed to form when 2 galaxies interact gravitationally with each other. The next galactic component is called the bulge. It is a central bright elliptical component of spiral and lens-shaped galaxies. It mainly consists of old stars moving on elongated orbits. The typical population of the bulge includes red giants, red dwarfs, or supernova, two types, as well as variable stars like Cepheids or globular clusters. For example, in typical lens-shaped galaxies, the bulge is larger relative to the galaxy's diameter compared to spiral galaxies. In my opinion, the bulge is one of the most interesting elements in the structure of galaxies. Now let's talk about the bar, or in layman's terms, the bridge. It looks like a dense and elongated formation consisting of stars and interstellar gas. It serves as the primary supplier of interstellar gas to the center of the galaxy. With this knowledge of the necessary components, we can now move on to classifying galaxies and learn more about these stellar islands. There are different classifications of galaxies, such as the Hubble classification or classifications based on infrared telescopes. Elliptical galaxies. Approximately 25% of all known galaxies are of this type. They are highly luminous and, from a distance, appear like giant shining spheres with the highest brightness at the center and fading towards the edges. Elliptical galaxies are nearly entirely composed of old stars, giving them a yellow or reddish hue. New stars are almost not formed in them, since the amount of interstellar gas and dust in them is negligible, although there are occasional exceptions. Elliptical stellar systems differ only in size and compression. They are classified based on their compression with letters E from 0 to 7. This number corresponds to the degree of flattening of the system. For example, E0 would be a spherical cluster, while E6 would be much more flattened. Moreover, according to the classification, an E0 galaxy can be perfectly round, while an E7 galaxy can be oval-shaped. The star formation in galaxies of this type has ceased for several billion years, and there is hardly any cold gas or cosmic dust left. Most massive galaxies are filled with very sparse hot gas with temperatures over 1 million kelvins. On the other hand, in spiral galaxies, star formation occurs more uniformly. Therefore, the most massive stars in elliptical galaxies have long completed their existence, while in spiral galaxies, new stars are constantly being formed and observed. One of the most common examples of an elliptical galaxy is M87. Spiral galaxies are the most widespread type and probably the most beautiful. They constitute more than half of all known galaxies. A spiral galaxy appears as a disk with a bright yellow ball in the center, around which spiral arms are coiled. These arms consist of fainter branches with a bluish tint due to the presence of specific stars, such as white and blue supergiants. In contrast to elliptical stellar systems, they possess several distinctive structural features. Spiral galaxies have spiral arms where active star formation processes occur. They have a stellar disk, which is a relatively thin layer of matter along the galaxy's plane, where the main mass of objects in the system and stars is located. Stars within the disk rotate around the center of the galaxy. In spiral galaxies, the presence of interstellar gas and dust, essential for star formation, is widely observed. Many spiral galaxies have a peculiar structure at their center known as a bar, from which the spiral arms extend. They are classified with the letter S and differ in the density of arm placement. Typically, these galaxies have 2 or 3 arms, although in some cases, the arms may vary in size. All of these arms, unless influenced by galactic collisions, are coiled in the same direction around the center of the galaxy, where most of the matter is concentrated, such as a supermassive black hole and dense spherical clusters of old stars, known as bulge. For instance, our own galaxy, the Milky Way, and the Andromeda Galaxy, which we will inevitably collide with in about 4 billion years, are both spiral galaxies. The Sun is located between the arms, away from the galactic center, and its velocity of movement is approximately equal to the rotation speed of the arms. This positioning allows the solar system to avoid dangerous regions of active star formation where supernovae often occur. It is worth noting that spiral galaxies are often observed beyond galaxy clusters. They differ in the degree of development of their spiral structure, which is denoted by adding letters A, B, or C to the S symbol. Galaxies with A have the main number of stars concentrated in a central bulge, while the central branches of the spiral structure are weakly developed or just indicated. In galaxies with B, the branches are more developed, and for those classified as C, the branches are well developed in galaxies classified as C. The main number of stars is contained in heavily developed and often scattered branches, while the central bulge has relatively small dimensions. The most well-known spiral galaxies include our Milky Way galaxy, the Andromeda galaxy, and the Bode's galaxy. An intermediate type between spiral and elliptical galaxies is the lenticular galaxies, classified as S0. In galaxies of this type, there is a bright, highly compressed central bulge that resembles a lens, while the arms are either absent or very weakly traced. Lenticular galaxies primarily consist of old giant stars, giving them a predominantly reddish color. They differ from elliptical galaxies because they have convexity and a thin disk, but they are distinct from type SAR because they lack a spiral structure. The main population of such galaxies comprises old and massive stars, mostly of red and yellow colors. 2/3 of the lenticular galaxies, like elliptical galaxies, do not contain gas, while in 1/3, the gas content is similar to that of spiral galaxies. Consequently, star formation processes, though present, occur at very slow rates. An example of a lenticular galaxy is the Spindle galaxy in the constellation Draco. More interesting are the so-called irregular galaxies, which do not fit into either the elliptical or spiral categories. Irregular galaxies lack any of the common forms and are usually characterized by chaotic connections, stellar clusters, and sometimes lack a distinct shape or pronounced center. They are relatively rare and make up approximately 5% of the total number of known galaxies. The reason why irregular galaxies differ so significantly from their galactic counterparts lies in the likelihood that each of these stellar systems was likely once an elliptical or spiral galaxy, but something disrupted their formation process or structure, leading to their irregular appearance. Such galaxies are mainly divided into two types: those that have some resemblance to a structure, allowing them to be classified into certain sequences of galaxies, and those that do not even have a semblance. There is also a third type known as dwarf irregular galaxies, characterized by a low amount of heavy elements and a large amount of interstellar gas, making them similar to the galaxies of the early universe. Hence, studying this type of irregular galaxies is crucial for understanding the process of galactic evolution. Moreover, in these galaxies, one can observe young, hot stars. They contain a significant amount of dust that blocks much of the light from the stars. It is likely that such galaxies have planets where the sky appears rather modest and dull. Personally, I would not recommend observing them through a telescope. Bright examples of such galaxies are NGC 1427A, or the Magellanic Clouds. As for the galaxies that possess certain characteristics but cannot be categorized into any of the aforementioned classes, they are referred to as peculiar galaxies. Their structural features can vary, such as distorted structures due to interactions with neighboring galaxies, the presence of dust lanes, ejections of matter, and so on. A classic example of a peculiar galaxy is the radio galaxy NGC 5128. Stars, planets, and cosmic matter, bound together by gravitational forces, form some of the most massive objects in the universe, galaxies. The exact number of galaxies remains unknown, but it is estimated to be several hundred billion, and that's only within the observable part of the universe. Despite galaxies being astronomically distant from one another, they sometimes collide. Such collisions are truly spectacular events on a grand scale. Cosmic evolution. In the universe, there are galaxies orbiting around a common center of mass. In such systems, there's a central giant galaxy with several satellite objects. During their evolution, if the orbits of smaller galaxies do not match, they all start to revolve around this center. However, if galaxies have identical orbits, they will merge into one large system, while the smaller object gets torn apart. Astronomers observe such collisions quite frequently. It is believed that the Andromeda galaxy also collided with a smaller galaxy in the distant past. Similarly, our system has also absorbed smaller galaxies. But if astrophysicists claim that the universe is expanding, why do galaxies collide? And all because the expansion of the universe is happening slowly. Galaxies in clusters and superclusters experience gravitational attraction towards each other and move at speeds of hundreds of kilometers per second. The cosmological expansion reaches such magnitudes only at distances of tens of millions of light-years, which is hundreds of times larger than the sizes of galaxies. Therefore, within clusters, galaxies do not notice the expansion of the universe. They move and collide as if it doesn't exist. However, no matter how common such interactions may be, astronomers rarely manage to capture dynamic images of colliding galaxies, like the ones Hubble captured. ARP 282 consists of the spiral galaxy NG69 and its smaller companion, IC 1559. They both have highly active cores, serving as powerful sources of radiation. The activity of ARP 282 is associated with the black holes located at their centers. Tidal interaction processes have led to a redistribution of matter within the galaxies, providing the black holes with abundant food. The galaxies have also formed a connecting bridge, which is visible in the Hubble image, consisting of elongated gas and dust affected by tidal forces. And that's not all. The Hubble Space Telescope also took a series of photos of two merging galaxies in the VV689 system, which astronomers have named the Angel's Wings. Unlike random visual alignments of galaxies that only appear to interact from Earth's perspective, these two galaxies in VV689 are in the midst of a collision. This galactic interaction has made the VV689 system in the constellation Leo nearly symmetrical, and now they resemble huge galactic wings. Another well-known space telescope, the James Webb, also captured interesting images. The star cluster in the Cartwheel Galaxy was formed as a result of a collision with a satellite galaxy. The Cartwheel Galaxy has two rings that expand outward from the collision center, much like ripples in a pond after a stone is thrown in. Due to these distinctive features, astronomers refer to it as a ring galaxy. It has a less common structure compared to spiral galaxies like the Milky Way. In the next two galaxies shown in the cosmic image, they pass through each other, leaving a bridge of young blue stars between them. The head-on collision between the two galaxies showcased an object of triangular shape where thousands of stars were born. This image was captured by the Hubble Space Telescope, as reported by NanoWork. Astronomers speculate that the galaxies passed through each other, triggering a fiery burst of star formation in a unique shape in NGC 2445, where thousands of stars ignite. This galaxy is rich in gas, the fuel from which stars are created, leading to its star-forming abundance. However, the new galaxy has not managed to escape the gravitational grip of its partner, NGC 24. The galaxy has pulled gas from NGC 2445, creating the peculiar triangle of newly formed stars. As we can see, these interactions can appear stunningly beautiful. In the search for dark matter, but it is not only the beauty that fuels scientists' curiosity. As early as the 1970s, serious arguments emerged in favor of the idea that galaxies contain so-called dark halos, apart from stars and gas. Theoretical arguments arose from considerations of the stability of the stellar disks of spiral galaxies, while observational evidence came from the large, non-decreasing rotation velocities of gas at the far edges of galactic disks, where there are almost no stars, and therefore the rotation speed is determined through gas observations. If the entire mass of a galaxy was primarily contained in stars, then the orbital velocities of gas clouds located beyond the stellar disk would decrease as the distance increased. This is observed in the planets within the solar system, where the mass is primarily concentrated in the Sun. However, in galaxies, this is often not the case, which indicates the presence of some additional massive and extended component whose gravitational field imparts high velocities to the gas clouds. The situation was partly clarified when massive dark halos were introduced into the mathematical model of galaxies. These dark halos do not contribute to the galaxy's overall luminosity and are only evident through their gravitational influence on the stellar subsystem. One way to obtain information about the structure of dark halos is by studying extended structures that form around galaxies during their interactions. For example, sometimes, during a close passage, one galaxy steals gas from another, winding it around itself in the form of an extended ring. The existence of extended polar rings can only be explained if the mass of the dark halo is approximately twice that of the luminous matter in the galaxy. Tidal tails also serve as reliable indicators of the presence of dark matter in the peripheral regions of galaxies. Perhaps the first evidence of hidden mass was obtained as early as 1933, when the astrophysicist Fritz Zwicky noticed that galaxies in the Coma cluster were moving faster than expected, implying the presence of some invisible mass that kept them from flying apart. The nature of dark matter remains unknown, so it is often referred to as some abstract cold dark substance that interacts with ordinary matter solely through gravity. However, due to its significant mass, it acts as the active background on which all scenarios of structure formation and growth in the universe unfold, while ordinary matter passively follows the proposed scenario. These ideas form the basis of the so-called hierarchical clustering scenario. According to this scenario, primary density fluctuations of dark matter arise due to gravitational instability in the early universe and then multiply by merging with each other. As a result, numerous gravitationally bound dark halos are formed, differing in mass and angular momentum. Gas collapses into the gravitational wells of these dark halos. This process is called accretion, leading to the formation of galaxies. The history of mergers and accretion of each dark matter clump largely determines the type of galaxy that emerges within it. The appeal of the hierarchical clustering scenario is that it describes the large-scale distribution of galaxies quite well. The most impressive numerical experiment conducted within this scenario is called the Millennium Simulation. Astronomers reported its results in 2005. In the experiment, the n-body problem was solved for 10 billion dark matter particles, starting from when the universe was only 120 million years old until the present day. During this time, nearly half of the dark matter had gathered into dark halos of various sizes, totaling about 18 million. Although complete and unequivocal agreement with the observations of large-scale structure has not been achieved yet, there is still much to discover. In 2002, a team of researchers led by Beth Willman began the search for unknown satellites of the Milky Way in the Sloan Digital Sky Survey. The first success came in March 2005, when a dwarf spheroidal galaxy was discovered at a distance of 300,000 light-years from us in the constellation Ursa Major. It became the 13th satellite of the Milky Way, with a record-low luminosity. All its stars emit light comparable to that of a single supergiant star, such as Deneb, the brightest star in the constellation Cygnus. The year 2006 turned out to be exceptionally fruitful for the discovery of satellites of our galaxy, when two other teams of researchers discovered 7 dwarf spheroidal galaxies around the Milky Way. And apparently, this is not the limit. Only recently, astronomers started to discover galaxies entirely devoid of dark matter or containing it in extremely negligible amounts. For example, the dwarf galaxy NGC 1052 DF2, which was discovered a couple of years ago by a team led by Peter van Dokkum from Yale University. Since then, several similar objects have been found, including DF4, located near DF2. These galaxies greatly puzzle scientists who are trying to understand how they could have formed without dark matter, or how they lost it. One hypothesis links their appearance to galactic collisions. In such an accident, the masses of their dark matter can continue their trajectory, passing through each other. However, clouds of ordinary matter experience pressure from each other, slow down, interact, and separate from the dark matter. This scenario is supported by an article published in the journal Nature by Van Dokkum and his colleagues. Observations of DF2 and DF4 showed that the trajectories of these galaxies started to diverge from a common point about 8 billion years ago. Moreover, other dark matter-poor dwarf galaxies also started moving along with them. Today, DF2 and DF4 are part of a chain of about 7 to 11 such objects, that located at a distance of about 70 million light-years from us. On the scale of star clusters, dwarf galaxies, and galaxies, collisions and mergers are constantly happening. Even our Milky Way is currently disrupting the Sagittarius dwarf spheroidal galaxy, which is its satellite. And in the future, this relatively small cosmic body, with only 1% of our galaxy's mass, will be completely absorbed. Looking further into the future, we can expect a collision and merger with the large Andromeda galaxy. According to scientists' predictions, the Milky Way and the Andromeda Galaxy will collide in about 4.5 billion years. And quite soon, in 3 billion years, Andromeda will approach us so closely that the stars of its galaxy will be visible to the naked eye. What will this collision look like? Thanks to the Hubble telescope's image, we can now visualize what the merger of the Milky Way and Andromeda will look like from the outside. A group of 3 galaxies, collectively named NGC 7764a and located in the Phoenix constellation at a distance of 425 million light-years from Earth, serves as a model for this scenario. Scientists are already running simulations of the collision between the Milky Way and the Andromeda Nebula on supercomputers. Data indicates that the Milky Way has absorbed smaller neighbors in the past. For example, some dwarf galaxies and globular star clusters were destroyed by tidal forces and transformed into star streams, with their stars likely to be eventually absorbed by our galaxy. Using data from the Gaia Space Telescope, scientists partially answered the question of when the last collision and absorption of a neighbor occurred. Gaia creates a 3-dimensional map of the galaxy by measuring distances to stars, enabling scientists to observe their movement directions. This led to the discovery that around 8 to 10 billion years ago, the Milky Way engulfed a sizable dwarf galaxy called Gaia Sausage Enceladus, GSE. As an inheritance from the collision, we received about 8 new globular star clusters along with 50 billion new stars. Additional research revealed that GSE was not a satellite of our galaxy, but was moving in a direction opposite to the Milky Way's rotation. Thus, our courses intersected and a collision occurred rather than a gradual merger. This intergalactic catastrophe provided us with material, forming about 50% of today's halo and 20% of the dark matter halo. The next similar event, as we mentioned before, will be the encounter with Andromeda. Scientists speculate that if the Andromeda Nebula and the Milky Way eventually merge, the resulting new galaxy will have an elliptical shape. It is even given a name, Milkomeda. By that time, the Sun, which might have transformed into a red giant, will be relatively far from the galactic center since the distance between stars will increase. However, this won't impact us anymore. What does this giant star reflect? You may have heard that the Sun is an incredibly large celestial body compared to the Earth, but there are even larger stars beyond that difference. The biggest of the biggest. What I'm going to introduce now is a star named Stephenson 218. This star is located in the same constellation as the number 1 star that had reigned in the past in the constellation of the Shield. The Shield star was considered the biggest star ever, but later it was determined that Stephenson was even bigger. This star is the first part of the binary system Stephenson 2, and it is located about 18,900 light-years away from Earth. It has rewritten a few records not long after its discovery. As you may already know, Stephenson 218 is the biggest star that humans could imagine. If we place this star in the position of our Sun, even Saturn's orbit would be within the star. 5 planets, including Earth, which is closer to the Sun than Saturn, would be swallowed by this giant star. In addition, Stephenson 218 is also one of the brightest stars in our galaxy. According to IAU standards, its brightness is even 440,000 times that of our Sun, depending on the calculation. However, there are times when it shows a more modest figure of only 98,000 times brighter than the Sun. Nevertheless, it is still an unusually bright star. If the Sun shone as brightly as this star, not only would we be unable to see anything, but the Earth would have been completely incinerated. Thanks to its abnormal luminosity, Stephenson 218 is visible even beyond the galaxy. If there were a civilization that developed somewhere in the Andromeda Galaxy, Stephenson 218 might have been one of the first stars discovered by extraterrestrial beings using telescopes. This star is exceptionally cool in this category, classified as M6.0 on the spectral type. Its temperature is not even close to that of an advertising light at 3,200 Kelvin. Typically, stars classified as red supergiants are hotter and are known to have temperatures of at least 3,500 Kelvin. Originally, this star is also extremely rare. It is not a very high rating for a red supergiant. Moreover, This star is too bright compared to its rating, and conversely, its temperature is too low. Of course, it cannot be denied that there might be a possibility that scientists made some miscalculations somewhere. However, if there were no errors in the calculations, this peculiar star will throw a big shockwave to the current scientific models, especially to the models related to the evolution of stars. What does this giant star reflect? When talking about various rare stars, the public raises one question: can life exist in that stellar system? However, for today's protagonist, there is nothing special to discuss as no planet has been discovered yet. However, we cannot assert that there are no planets simply because we have not found any. Therefore, let's imagine what kind of planets could exist around this star and what possibilities there are. First of all, Stephenson 218 was not originally in its present state. We need to keep in mind that from birth, there are no red supergiant stars. Stars become red supergiants as they age, including our Sun, which will follow the same fate, although it won't become as massive as others. We don't know what kind of genius this star was before becoming a red supergiant, but it was probably a massive star with a similar spectrum to our Sun, and it would have remained in that state for billions of years, providing enough time for life to emerge on planets in its system. At that time, this star was not particularly large, at most 2 to 3 times the size of the Sun. Although it was not as bright as other stars, considering other characteristics, it would have had a relatively large and bright habitable zone. There may have been more than one planet within the habitable zone. In other words, there is a good chance that life existed in the Stephenson 218 system. There is a possibility that there are multiple planets with such conditions. In that case, what are the chances of discovering intelligent life by discovering a way to travel between stars and visiting the present time? Unfortunately, the probability of that happening is low. When this star began to expand and take on its current form, the planets inside the heavy-tailed zone would have been swallowed up. In addition, the brightness of this star has been increasing since long before that, causing the planet's surface to turn into a sea of lava. In other words, even if the planet itself still exists, all Earth-like life forms will have perished. However, there may be sharp viewers who raise a question here. As the star expands and becomes brighter, wouldn't the heavy-tailed zone widen? Moreover, even if a planet near the primary star was destroyed, couldn't a celestial body that was far away until now become one instead? When the binary system was young, the farthest edge of the star system was trapped in a hellish cold similar to Pluto in the solar system. However, after the star became a blue giant, the temperature rose and it became warmer. If there was sufficient gravity, there might have been the possibility of liquid water or atmosphere appearing there. However, there is one problem. The star's blue giant phase is an extremely short period in astronomical terms. It might be enough time for life to be born, but it would not evolve. Additionally, if there were planets in distant regions that had deep oceans under an ice cap like Europa and life existed there, it would be destroyed due to global warming. The ice cap would melt and the oceans would become vulnerable to radiation from space. In other words, if there were organisms including intelligent life on Stephenson 218, they would not survive. Even if it existed, it seems that it perished a long time ago. At best, we can only assume that an intelligent life form moved to another star system with a longer lifespan. As I mentioned before, the fate of a star in its red supergiant phase is very short. As the star expands, it can no longer maintain the outermost layer of gas due to its gravity, and the gas is scattered into space. As the star's mass decreases, so does its gravity, which means it cannot retain a lot of material. The star cannot stop melting away, and eventually, it will become a white dwarf, leaving only its core. That's all for today's video. Thank you for watching until the end. I hope you enjoyed the video. To summarize, we are living in a perfect time to observe rare stars like Stephenson 218. By studying this star, we have learned a lot about the fate of other stars, including our own Sun. Unfortunately, with our current technology, we cannot send a probe to explore this star, but we can still enjoy many other interesting events in space, including aliens.